Corollary 11.10.3. And this corollary is going to generalize our previous theorem, which was about a piecewise constant function f. This time, in place of a piecewise constant function, we have a Riemann-Stieltjes integrable function. Otherwise, the statement is same. I mean, the beginning is exactly same. Here also, you have a monotonically increasing function alpha, which is differentiable, and its derivative alpha prime is Riemann integrable. But in place of a piecewise constant function, you have a Riemann-Stieltjes integrable function f. Then conclusion is same. F alpha prime will be Riemann integrable, and the Riemann-Stieltjes integral of f will be equal to the Riemann integral of f alpha prime. So let's now see the proof. So actually we have two integrable functions. One of them is alpha prime, which is Riemann integrable, and as such it is bounded. And the other one is f, which is Riemann-Stieltjes integrable, so that is also bounded. So that's how we start the proof. Since f and alpha prime are bounded, so is their product. The product is also bounded. So we have at least one thing about f alpha prime that we would like to have in the beginning itself, which is its boundedness. Now we need to prove that it's Riemann integrable, and the Riemann integral is this. Now alpha is differentiable and it's monotonically increasing, so the derivative will be a non-negative function. Since okay, so alpha prime is non-negative. Now we are going to choose an epsilon. That's what we do in analysis, right? Every now and then an argument starts by choosing an arbitrary positive epsilon. There exist PC functions. For this epsilon, there exist PC functions f underscore and f bar on this interval such that, let me first write what I want to write and then I will explain. And d alpha minus epsilon is less than d alpha, which is less than or equal to f bar d alpha, which is strictly less than Now what is all this? Well, Now we go back to the part of the hypothesis that f is Riemann-Stieltjes integral. This means what? This means that the lower Riemann-Stieltjes integral of f is equal to the upper Riemann-Stieltjes integral. Now let us first of all concentrate on the lower integral. What is the definition of the lower integral? The lower integral by definition is the supremum of a set, is the least upper bound of a set. This is what it is. It's the supremum of what? A set of integrals g d alpha such that g is piecewise constant and g minorizes f. Okay, so this is what the lower Riemann-Stieltjes integral is. Supremum means what? Least upper bound. That means this thing which actually, forget about the minus epsilon, only this integral which is just this is the least upper bound of this set. But if we go even smaller than the least upper bound, lower than the least upper bound by subtracting a positive real number epsilon, then this is no longer an upper bound of this set, which means what? That at least one element of this set will exceed this number, will be greater than this number, strictly greater than this number. But what type of elements does this set have? The elements are Riemann-Stieltjes integrals of piecewise constant minorizing functions. That is why there will exist at least one minorizing piecewise constant function, which the author has called f underscore, whose Riemann-Stieltjes integral will exceed this. Okay. Similarly, if you consider the upper integral, that is this one, the upper Riemann-Stieltjes integral of f, then it will be the infimum, the greatest lower bound of another set that is slightly different. It's the infimum of Riemann-Stieltjes integrals of again piecewise constant functions, but this time those that majorize f. Okay, infimum, that means greatest lower bound. Now to this quantity, this integral, or the same thing, this integral, you add epsilon, then you become even greater than the greatest lower bound. So this larger quantity can no longer be a lower bound of this set, which means what? That at least one element of this set will be strictly less than this quantity. And that's why at least one piecewise constant majorizing function will exist, whose Riemann-Stieltjes integral will be less than this. And f bar is one such majorizing PC function. Okay, whose integral is less than this. What about this middle inequality? The middle inequality, of course, comes from the fact that if you ignore this middle term f of x, and concentrate only on f underscore and f bar, you get the fact that these two PC functions, both of them are PC functions, are like this. F underscore is less than or equal to f bar throughout the interval. So by one of the properties of Riemann-Stieltjes integrals of PC functions, their integrals will also satisfy another such inequality. That's how the middle inequality comes. But now, in place of this, did I miss something here? No, okay. Now, in place of these two middle terms of this series of inequalities, we can write something else. Integral of f underscore alpha prime, and in place of this, integral of f bar alpha prime. How? By the previous theorem. Note that f, unlike f, which may or may not be piecewise constant, but f underscore and f alpha prime are piecewise constant, and that's why to these integrals we can apply the previous theorem. Now, by theorem, so this one is the third item, so that's the second one. 11, 10, 2. This is what we are going to get. This is less than integral of f underscore alpha prime in place of this, and in place of that, integral of f bar alpha prime, which is strictly less than this. Let us recall very carefully what this theorem says. This theorem doesn't merely, of course, whenever you write these integrals, already it's within this notation itself, it's included that f underscore alpha prime is Riemann integrable, and this Riemann integral is equal to this Riemann-Stieltjes integral. Similarly, f bar alpha prime is also Riemann integrable. Remember this, okay, we are going to need it. Someone may suddenly get confused seeing Riemann integrals and Riemann-Stieltjes integrals simultaneously occurring, but do not forget that no matter how complicated these notations look, each term here is after all some real number. That's what they are. Alright, now we again go back to the relation between f, say f underscore and f. F underscore is the PC function which minorizes f. Since this is less than or equal to f, and this we saw in the first paragraph itself, and this is non-negative. So that is why we have alpha prime less than or equal to f alpha prime. You do understand the interpretation of this inequality, right? It's not saying that the function f underscore is less than or equal to f. This is just a shorthand way of writing that f underscore of x is less than or equal to f of x for all x in that interval, in the domain of these functions. Okay, so that's how we have this inequality. Now what we want is to take lower Riemann integrals on both sides of these inequalities. And still then we will have another such inequality, but how? Let Let us go systematically. Okay. Let S1 be the set of all Riemann integrals of functions g such that g is a piecewise constant function on this interval and g minorizes this. Okay. And let S2 be the similar set for this other function. That means this is the set of all Riemann integrals of functions g such that g is Pc on a comma b and g minorizes f alpha prime. Now, what is the relationship between S1 and S2? If we notice carefully, S1 is a subset of S2. Why though? You take any element of S1, it's going to look like this. It's an integral. That means it's a real number. But what about this g? This g is a PC function on this interval that minorizes this. However, this itself minorizes this. So automatically that g will minorize this as well. And so this integral of g by definition of S2 is an element of S2. So every element of S1 is in S2 and that's why S1 is a subset of S2. Since S1 is a subset of S2, we have supremum of S1 less than or equal to supremum of S2. Why? Well, the supremum of S2, whatever it is after all an upper bound for the set S2, which means that every element of S2 is less than or equal to this. In particular, because the elements of S1 are also inside S2, so each one of them also is less than or equal to this supremum. That is, supremum of S2 is an upper bound for S1 as well. May not be the least upper bound for S1, but it is an upper bound for S1. So the least upper bound of S1 will be less than or equal to this sum upper bound. That's how we get this inequality. But what are these suprema? This supremum, by definition of lower Riemann integral, is the lower Riemann integral of this function alpha prime, and this one similarly is the lower Riemann integral of f alpha prime. Or remember, I asked you to remember that this f underscore alpha prime is Riemann integrable, which comes from the previous theorem. So that means its Riemann integrability tells us that this lower Riemann integral is equal to just Riemann integral. So we can now write in place of this just ordinary Riemann integral. You cannot, however, change this because we don't yet know whether f alpha prime is Riemann integrable. In fact, that's what we are trying to prove. So this will continue to be the lower integral. But we saw in those previous inequalities that this quantity is greater than, strictly greater than the Riemann-Stieltjes integral of f minus epsilon. Hence, this will be strictly less than this, and that's why it is less than this. Similarly, instead of working with f and f underscore, if you work with f and f bar, you would have gotten this. The upper Riemann integral of f alpha prime is strictly less than the Riemann-Stieltjes integral plus epsilon. However, we already know that this is less than or equal to this, because this is lower Riemann integral and this is upper Riemann integral. Well, how do you see that also needs a condition? That's not true for just about any function. We need the function to be bounded for these these lower and upper integrals to be real numbers. Is it bounded? Yes. In the very beginning itself, we wrote why it is bounded, because f and alpha prime are both bounded, and that's why this will be less than or equal to this. That is, so now we can combine those two inequalities. That means f d alpha minus epsilon is less than this, which is less than or equal to this is less than plus epsilon. Now epsilon is arbitrary, so we can not write epsilon and still have similar inequalities, except these strict inequalities will turn into ordinary inequalities. Since epsilon is positive and is arbitrary, so this will be less than or equal to the lower integral of f alpha prime, which will be, we are almost there. But you see the first and last term of this chain of inequalities, they are the same, and it's a real number. That's why these two also have to be equal and has to be equal to this only. Hence, if alpha prime is, but equality of lower and upper Riemann integral tells us that if alpha prime is Riemann integrable, have this. So that's the proof. There are 3 more results which will, in steps take us towards the full result, which allows us to make substitution while doing integration. There is a remark after this corollary. The remark basically says that, roughly speaking, this above theorem tells us that f d alpha is f times the derivative of alpha times dx. The notation that we use in this book does not mention that dx when we are talking about Riemann integral. But if we did, then it would look like this. Although in this book we do not attach any meaning to this type of things, any separate meaning. For us, for example, f d alpha does not really have any meaning, but they do mean something. If you know about differential forms, it will come at some point, not in this book, but somewhere else in analysis we will see differential forms. There, those things are rigorously defined, and there f d alpha, this expression itself takes on a meaning. And if you see that definition, then you will understand why this equation is not simply something that we used to do in school without really understanding what it means. It really has a definite meaning. And integrating differential forms, if you look at some expression like this, now f d alpha, it makes sense to integrate this form. That also has its own meaning, which again give you this type of things. So, but from another point of view. So let me just stop the video here itself. What do we have tomorrow? Oh, number theory. We have already kind of completed one exercise set. So tomorrow we will start Wilson's theorem. Okay, so see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.